Hi everyone. I want to spend a couple of minutes talking about fact, law, and theory. These are words that are used all over in science. And one of the fun things that I find challenging is they have very different meanings in science than in everyday English. And so we're going to spend a few minutes talking about, in the worlds of science, what does fact, law, and theory actually mean? Now, a fact in science is an indisputable piece of information. Anyone who is an educated person agrees that this is a true piece of info. For example, acceleration of gravity is 9.8 meters per second per second. That is near the surface of the Earth, independent of mass. Lots and lots of thousands of experiments have been done, and that is what we get for the acceleration of gravity. Carbon atom contains 6 protons. An oxygen atom is going to contain 8 protons. Those are facts. That is part of the definition of what it takes to be carbon, or what it takes to be oxygen. And the Earth revolves around the sun. Now, hundreds of years ago, people did not believe this, but a lot of scientific inquiry, an awful lot of observations have been made, and anyone who is educated in the world of science agrees to this. Now, will you find people who today even who say this is hooey? Well, yeah, because not everybody is educated in science, but that's what we mean by fact. This is not anything open to debate or speculation. Can we find the acceleration of gravity more precisely out to more digits at different locales? Absolutely. But these are pieces of information that anybody who's a scientifically trained person is going to agree upon. A law. When we use the term law in science, this is a description of how nature behaves. We are just describing nature does this. And laws in science are different than laws in the legal community. Now, a stop sign, for example, is a regulation or law that has been developed by man. This is just, we all agree to obey that law to make driving safe. But this is not the way it works in science. In science, we discover laws. The laws of nature already exist. And the purpose of science is to uncover those laws. For example, the law of gravity. The law of gravity, this is Newton's universal law of gravity. It is a mathematical equation. Newton's second law of dynamics is F equals ma. These are rules that we have done experiment after experiment and found that nature obeys those. Law of conservation in energy. As long as you stay away from a nuclear sort of situation, the amount of energy you put into a system is going to be equal to the amount of energy that you get out of a system. Energy cannot be created or destroyed. It just changes forms. All of chemistry is based on the law of conservation of mass. The amount of mass before a chemical reaction is going to be equal to the amount of mass after a chemical reaction. Now, as I mentioned, these two do get a little bit different when you get into a nuclear environment, but we're not going there for this moment. So laws are just descriptions of how nature behaves, often an equation and sometimes just a statement that what you end up with in the beginning is what you end up with in the end. Now, another term you're going to hear is the term principle. Principle of conservation of momentum, the uncertainty principle. What is principle in science? A principle is not as all-encompassing as a law. Principles are guidelines that we've discovered that nature follows, but the sphere of where they're useful is much smaller. For example, law of conservation of energy, momentum, says momentum before something like a cannon going off and momentum after a cannon goes off are going to be the same. But principle of conservation of momentum is only useful in action-reaction pairs. Something happens here and something happens there. Collisions and explosions. It's got a real small, narrow range where it can be used. The uncertainty principle. Heisenberg's uncertainty principle says that you cannot know both the position and the momentum of subatomic particles with great accuracy. As you get the momentum more specific, the position gets more out of whack. And that is a principle that's followed by subatomic particles, but it is only terribly useful in the subatomic realm. If you're talking about a pickup truck, well, this is not terribly useful. So principles describe nature, but they're in a smaller group of things they're describing, not everything in the universe. A theory. Theory is the term in science, I think, that is most misunderstood in the English language. Now, if I say I have a theory about why a certain couple broke up, and I might say, well, you know why they broke up, he ate too much peanut butter and never replaced it. Okay, that's just a silly, uninformed guess. And that's what a lot of people think when they hear the term theory. They put it in the same sort of realm as gossip, or somebody's bright idea without any sort of evidence, and that cannot be further from the truth. In science, a theory is a big story used to describe a big idea backed up with gobs of evidence. So here are some examples of theories. Cell theory, the fact that all living objects are made out of cells, and how do those cells gain energy, and how do they respirate, and how do they have energy go into and out of the cells, and how do the cells reproduce. All of those are pieces of this big idea, which is things are made out of cells. Gobs and gobs of experiments about cells, plant cells, DNA as part of the cell, living cells, embryos, how they develop, all of that is incorporated in cell theory. Germ theory, the concept that viruses and bacteria are part of these little microscopic things that can make us sick. And if you just walked into your doctor and said, oh, I think germs are theoretical, he or she is just going to look at you and go, no, but they're going to treat you anyhow because they're good people. Now, when you start talking about things like Big Bang Theory, people go, oh, I still think that's just a bright idea, but it's not. It's a big story to describe the big idea of how the universe began and what we actually see in that universe today. Gobs of pieces of evidence, including Doppler effect and Hubble constants and the W map of the early universe. Lots of pieces of evidence. Now, do these theories change? They change? Yes, they change. But what has happened is they get more finely tuned. It's sort of like a jigsaw puzzle, and maybe there's a couple puzzle pieces missing. And as we do more experiments, we are able to fill in another puzzle piece here or there as we learn more to help make the theory more complete. Theory of evolution. Another one that a lot of people go, oh, I just think it's theoretical, but it is a huge story of how life came to be and how life came to have all of the variety that we see on planet Earth today. There are massive amounts of scientific evidence for these. So you are becoming a scientifically educated person, and I hope this helps you understand fact, law, and theory.